Okay, so we can start again. In the last lecture, we spent some time looking at the calculation of the angular power spectrum in the toy model, and the goal was to get used to the notation that's used in the literature in the calculations of the CMB angular power spectra on the one hand, and on the other hand, it was to have a basic toy model where you see what I think are the most prominent features in the angular power spectrum of the cosmic microwave background, which are the acoustic oscillations and the silk damping. It's clear that that toy model doesn't capture everything, so we then spend some time discussing how you put gravity back. This, on the one hand, enters through the collisionless Boltzman equation, because photons now have to move along geodesics of the space-time metric, and it also enters through the equivalence principle in collision terms, so you just write everything in a covariant fashion. And the other thing I sketched toward the end of the lecture was how you reincorporate the photon spin, and so that eventually then has all the ingredients of the full Boltzmann equations. And instead of writing them, I thought maybe it's okay to just show them to you on the slide so you can look at them. And what you see is what we discussed. So here is the free streaming part of the Boltzmann equation, so the collisionless Boltzmann equation, or the part of the Boltzmann hierarchy that represents that. The only difference in the expanding universe is, before in our toy model we were always working with the physical momentum of the particle. The physical momentum in cosmology can be written, as we saw, as the co-moving momentum divided by the scale factor, so that side should look familiar. Then we had the collision term here that represents scattering of photons out of the line of sight. This one was the guy that we had was representing the scattering of photons into the line of sight. We also had the coupling to the baryons, so if the photons and the baryons are tightly coupled, they move with the same velocity. This is the contribution that you get from the part of from the collisionless part of the Boltzmann equation that represents that the photons move along the geodesics of the space-time metric. So this is the A and B that I introduced yesterday in the scalar vector tensor decomposition of the metric. And so those are the ingredients that we all saw already. And then the only difference is this guy. It's sometimes called a source function. It looks like this. And the reason it arises is just because the Compton scattering isn't isotropic like I assumed in the toy model, but it's given by the Klein-Nishina formula. And so you have this additional contribution here from the dependence on the polarization. Similarly, for the delta P, for the polarization of the photon, there's a similar Boltzmann hierarchy. Again, there's the free streaming part, and then there's the collisional part. Again, this is the thing that's just describing the scattering out of the line of sight, and it tends to isotropize the photon distribution. And you can see that from the fact that the -1 here is 1 is larger than 1/2 for the 0 component and 1/10 for the delta L equals 2. So all the polarization, the scattering tends to erase the polarization. The one contribution that you see in the source function that is different from delta P's here, so you have a temperature quadrupole, and it's relatively easy to understand why is the quadrupole that sources the polarization. So I'll try to explain that on the board, mostly without equations, just with some pictures. There's not much you have to know, so let's assume there's an electron sitting here, and the only thing you have to know about scattering of photons of electrons is that the scattering or the outgoing radiation is predominantly polarized transverse to the plane in which the scattering appears. So if you imagine that there's a photon coming from here, it scatters off the electron, and then you see the outcoming radiation, so it scatters in your direction, then as I said, the outgoing radiation is predominantly polarized just from the Klein-Nishina formula, predominantly polarized transverse to the plane in which the scattering occurs. So in this case, you would get outgoing radiation that's polarized in this direction from the single scattering event. then if you think of the, well, this is, you probably know this because this is how the polarized sunglasses work, except there you would think that the sun sits up here, so you're trying to block out the polarization in this direction. If you have a single photon, then you get polarized radiation, but this electron is sitting in a bath of radiation. And if you, for a second, assume that it's isotropic, so you only have a temperature monopole, then you get photons scattering from here. The outgoing radiation is polarized in this direction, but you have the same number of photons that come from this direction, and so the net effect is to have unpolarized outgoing radiation for an isotropic radiation field. Then you can ask what happens if you have a temperature gradient. So let's say that, so the electron is still sitting here, but let's assume that you have hotter radiation over here. So there's more photons over here, let's say, than on this side. Then what happens is you scatter, again, from these photons will scatter off the electron, and there will be some amount of polarization. Here there's fewer coming from this side, which will add a little bit, but not all that much. But then it cancels the effect, again, from these guys, because you have more here, fewer here, so it's the same number of photons as you get from these sides. So the net effect for temperature dipole is still that you get unpolarized radiation out at the end of the day. But if you have a quadrupole, so if you have hotter radiation over here and hotter radiation over here, hot just means, I mean, the number density of the photons goes like the temperature cubed, as you know. So you have more photons scattering the electron from this side and from this side than from these sides. And so it's predominantly now polarized in this direction because there's fewer photons from the other side. So the outgoing radiation is predominantly polarized in this direction in this case. And so you can see that it's really the temperature quadrupole that sources the polarization of the cosmic microwave background. And yeah, so that's why this is the relevant piece for the polarization. Does that make sense? It's relatively simple, so the only thing you have to remember really is that the outgoing radiation is predominantly polarized, transfers to the plane in which the scattering appears. And so then the next question was, so this is really the full set of, I mean, Boltzman hierarchy. There's nothing else. These are the equations that are in the codes. Then the next question was how you include neutrinos, but that's also easy to do because the neutrinos also can be described in the same way as we did with a phase-space density, and you get again the free streaming part that we derived. And then if you work out, we didn't quite work this out in detail, but we wrote down the collisionless Boltzmann equation in the presence of non-trivial metric. And so if you work it out in terms of the metric perturbations, you just get this contribution along with it that represents the fact that also the neutrinos propagate along geodesics of the space-time metric. Then if you want to include the baryons, you could include them in the same way, but they're non-relativistic. And so then, as we briefly discussed in the discussion yesterday, that means that all the higher multiples are really suppressed by the velocity, or v, over the speed of light. And so the only two contributions that survive from the Boltzmann hierarchy in this case are the energy conservation. This is the equation for delta T0, which you kind of recognize. I mean, this was the delta T0, delta rho over rho. If you write it, then this actually goes away, and you just get delta rho over rho dot, because rho goes like 1 over a cubed, so it cancels this piece. And this was the delta T1 here. And this is again just the motion along geodesics. And then this is the delta T1 component, which is just eventually momentum conservation and is responsible for the photons and baryons tracing each other if the scattering is efficient. So if this is large, this gets effectively set to 0 by momentum conservation. For the dark matter, it works in very similar ways. You just get the same equation as for the baryons, except they don't couple to the photons. And then you still need some equations from, or you keep some of the equations from the Einstein equations. This one is effectively the Poisson equation. So you see you have the Laplacian acting on the metric perturbation as 8 pi g times the perturbation in the energy density. And then you need one more equation. There's different options you could choose, but this is one that's convenient because it's a simple equation. And so these are the equations that are really implemented in the codes. And if you want to modify anything, if you want to include dark matter interactions, you would do it here. You would just modify these equations, work out what the collision terms look like in your field theory, and just work it out. And I'll apologize for using the slides, but I also still want to talk a little bit about data analysis, and I was worried that I run out of time in that way. But we really looked through these things in some detail. So those are the relevant equations, and then quite what is solved. So you could solve those equations directly, but then if you want to calculate angular power spectra up to L of 2000, let's say, you have to solve this hierarchy all the way up to L of 2000, whereas from the formula we wrote yesterday, and we can also see it here, there's a better way of doing it, and this is what the codes actually do. So way back when, there were codes that actually did that, so you just solve the Boltzman hierarchy all the way for very high L. But now what is done is you use what is called as the line of sight integration, and it's based on the formal solution to these equations that I briefly mentioned. So if you look at that equation, this is of the form that I sketched on the board. It's just f prime times plus some function times f plus some other function, so these guys here. And you can formally integrate those equations, formally just because the delta t still appears on the other side, so you can't directly work with it. But you see that if you look at this equation, there's only low multiples of the delta t0 appears here, and then there's delta p0, delta t2, and delta p2 in here. And there's the delta u, which is delta t1. So it's only up to L equals 2 that appears here. And so what you can do is you can solve the Boltzmann hierarchy up to fairly low L. Usually it's truncated around 20 just to make sure you get the lowest multiples accurately. And then you can get all the other ones by using this expression to integrate this. And so that's computationally much more efficient because you're not keeping track of the full Boltzmann hierarchy, you're only keeping track of the lowest multiples and then computing the other ones through this line of sight integration. So that was a big step forward. This is what CMB Fast did by Matthias Saldarriaga and Uroš Seljak. The one thing that's missing still, so these are the equations, then the question is how do you actually set the initial conditions? And the one thing that's important to keep in mind is if you look at the equations, there's two scales in the problem. So there's the Hubble rate, just how fast the universe expands. And then there's the momentum of the Fourier modes. And this guy just scales like 1 over A. Hubble, we know, scales like 1 over T, but we also know that during radiation domination, A scales like T to the 1/2, so T scales like A squared, which means that Hubble here scales like 1 over A squared, and here it scales like 1 over A to the 3/2, but in both cases it drops more steeply than the momenta redshift, so as you extrapolate backwards in time, so now what we observe, obviously the wavelength of modes that we observe are much smaller than the Hubble radius, but as you go backward in time, it turns out that the modes were what people call outside the horizon, so the wavelengths are larger than the Hubble radius, and during that period, the equations simplify quite a lot, and this is where you set the initial conditions. And it's not difficult. I mean, but takes a little while to work out. I mean, but it's something you can just sit down, take those equations, take the limit, and you see that there's a solution where all the perturbations are proportional to each other. All the density contrasts are the same density contrast in photons, neutrinos, cold dark matter, baryonic matter, and all the velocity potentials are the same. And all the higher multiples go to 0. This is what are called the adiabatic initial conditions, and then you really get a very simple system, and you can figure out the solution, again working in this limit where you assume that Q over AH is small, and you get a solution that looks like this. So it's just to show that you can work it out. It doesn't take long if you put it in Mathematica. If you do it by hand, maybe it takes a little bit longer, but it's not in general difficult, and you just get some set of initial conditions. This is not the most general set of initial conditions. There are, you could depart from this ansatz, and those are what are called isocurvature modes. There's no indication in the data that isocurvature modes are excited, which is why I'm focusing on the adiabatic initial conditions. So all the data is consistent with this assumption, and this is also what something like inflation typically would set up. So in practice here, you can set them at pretty much any time as long as the modes are outside the horizon, because this quantity here that sets the initial conditions is constant as long as the modes are outside the horizon. So in practice, you would set it sometime at temperatures below 10 to the 9, because that's when the system of equations we're writing actually makes sense, because at earlier times you would have to keep track of electrons, positrons, and so on. So at that point, it's still true that this quantity is conserved. So there's a paper by Steve Weinberg that shows that it's really conserved under very general assumptions. But it's more convenient to set them as late as possible, which is, I guess, some time when Q over AH is, let's say, 10 to the minus 3. So when these modes are outside the horizon, but not too far outside the horizon, so you don't have to, so you can still work in with the system of equations that we've been writing. Yeah, but this property that this thing is constant is important for that statement. So it's really, as long as the modes are outside the horizon, they don't evolve. They're just frozen, and then they start oscillating as they enter the horizon, as Q over AH becomes large compared to 1. And so this is really what's done in the codes. So the codes that people use exactly implement that's the set of equations that I was showing you, and then implement that set of initial conditions, and that's what, when you compute the spectra, this is what the codes did for you. I'm showing the two most commonly used ones. There's CAMP by Anthony Lewis and Anthony Challoner. It's written in Fortran. And then there's a class, which is written in Z by Julien Lescourg. And so it just is a choice of whether you want to work with the Fortran or the C version. This is the one that's usually used by Planck, but it's been checked that both reproduce the same results. So you can use whichever one you like better. Okay, any questions about these parts so far? If there's no questions, then I'll discuss in a little bit more detail what we already discussed in the last lecture, which is what the different components are that you're seeing in the angular power spectrum. And this time I'll discuss it for the full set of equations, not for the toy model. And the first thing to notice is that if you look at this line of sight solution that I already wrote before, it breaks up into two pieces. The first one is one where everything is multiplied by omega c, which is again the rate at which these things scatter. It's NE times sigma, the Thomson cross-section, times the speed of light. And then there's a contribution that's not proportional to omega c. Those two are usually referred to as the contribution from the last scattering surface and the integrated Sachs-Wolf effect. And so we'll look at them separately. This is the one that's coming from the last scattering surface. This is the contribution from the last scattering surface. And the interesting thing to notice, or the reason we call it last scattering surface, is that this is proportional to the probability of last scattering that we derived. So remember, in one of the earlier lectures, we derived that the last scattering probability was given by NE sigma tau e to the minus t to t0 dt NE sigma tau, and this is exactly what's there. So this is what I'm calling omega c in the slide. So this is something we saw. And so this is in the toy model. I just set this thing to a delta function. In general, this is how it appears. So it appears as a convolution in this way. And this looks, so the contribution that arises from last scattering is shown here. So the black one is the full angular power spectrum, and the purple one is the contribution from last scattering. So this is the one that we modeled in the toy model. The ISW contribution is the one we were missing. And then if you look at it in more detail, this is also something I already showed you in the toy model. You have this contribution, which are the intrinsic density fluctuations. The new piece that's added in the presence of metric perturbations is this one, and the physical interpretation is just that this is some gravitational redshifting. So if you have photons that are in a gravitational potential, they have to redshift and make their way out of the potential. But it's only really this combination that's gauge invariant, which is why I'm circling the whole thing, so you can change your coordinates to shuffle things around between gravitational potentials and density perturbations. But there's this entire contribution that's gauge invariant. And then similarly for the Doppler contribution, you can shuffle things around between the two pieces, but this as a whole is the gauge invariant quantity and just represents the Doppler effect from the motion of the plasma. And this is again indicated by the mu here, which is the direction, the q hat dot n hat, indicating that there's a Doppler effect when it's moving toward you, but not when it's moving sideways. And so these are the contributions. This is the cosine contribution that we computed in our toy model. This is the Doppler effect, and then they add and get squared, as we saw yesterday. So these are the two contributions. And the integrated Sachs-Wolf effect then is everything that doesn't arise from the last scattering surface. It's missing the omega c, so you see that this also arises even if there's no free electrons around. So this can arise at later times, and we can look again at what that contribution looks like. So it looks like this, and it's interesting to understand the physics for that a little bit better. So there's this contribution for the metric perturbations. There's no contribution if this vanishes, and it turns out this is, so we were working in synchronous gauge. You can go to a different gauge, you can go to the Newtonian gauge, and then you see that this is the Newtonian potential, and you can show that in the matter-dominated period, the Newtonian potential doesn't evolve. So there's no contribution to this from the matter-dominated period, but there are two effects. One is at early times, because at the time the CMB last scattering occurs, we're at a redshift of 1100. We saw in our estimate that matter radiation equality happens at about a redshift of 3000. So at a redshift of 1100, we're not yet quite completely matter dominated. There's still some remnant of the radiation, so there's some contribution from radiation at early times around last scattering that leads to an effect. This is referred to as the early integrated Sachs-Wolf effect. And then there's a late time effect from when the cosmological constant or dark energy takes over. So this is again when the potentials start to decay and when you get another contribution, and you can break up the two contributions to the angular power spectra, and you get the late time contribution that only really contributes at relatively low multiples, below, let's say, L of 20 or so. And then you get the early ISW contribution that contributes around L of 100 to 200. So those are really the various pieces. So if you look at the angular power spectra, now you hopefully have an idea really what goes in. So there's the Doppler contribution, the Sachs-Wolf contribution, and then the early ISW and the late ISW. So this is what they all look like. And the one effect, so this is when you add them all up, all the early contributions from around the time of last scattering and the late contribution. So most of the effect, or most of the spectrum, is really generated at the last scattering surface. So the CMB really predominantly knows about what's happening at a redshift of 1100, and only slightly from the late times what's happening at lower redshift, except I'll talk a little bit about lensing in a little while. But that's the only other way that it knows about the late time effects. And then the one difference you might notice between what I'm showing here and what I'm showing here is coming from the fact that eventually at low redshift, let's say, at low redshift, let's say starting at redshift 8 or so, redshift 10, 8, we're not sure exactly where, but the universe becomes reionized, so there's free electrons around again that the CMB photons can scatter off of, and that leads to a suppression. So some of the CMB photons scatter out of the line of sight. There's also some that scatter into the line of sight, but this is then an effect on large angular scales. So this enhances what's going on large angular scales, but suppresses what's happening on small angular scales by a factor of e to the minus 2 tau. So that's all I wanted to say about the primary anisotropies. So hopefully you have some idea of what the ingredients are for the spectra. But are there any questions about these parts? Okay, if not, then I wanted to say a few words about things beyond the primary anisotropies. So these are the intrinsic things, intrinsic to the CMB. Now we'll talk a little bit about things beyond the intrinsic CMB, just because the CMB data really isn't just a map of the CMB, but these are really maps just at different microwave frequencies, and so there's additional stuff in these maps. This is shown from COBE. This is from WMAP at 5 frequencies, 23 gigahertz, 33, 41, 61, 94, and then Planck at 9 frequencies, from 30 gigahertz to 857 gigahertz. So this is what the data really looks like, and I'll say a little bit more where you can find it and how to actually analyze it in a little bit. But the point is, on the one hand, that if you want to learn about the CMB, you should also understand some of the other stuff that's in the maps, like the galactic dust. This is something that you see very clearly by eye in the Planck data as you go. So here, this is somewhere between 70 and 100 gigahertz is where the foreground emission is minimal. Then as you go to higher frequencies, what's emitting is predominantly dust from the galaxy. And at lower frequencies, you see synchrotron radiation from the galaxy. Those are very prominent. And then there's also emission from line emission from molecules. I'll say a little bit more about that also. Then there's the cosmic infrared background, which is emission from far away dusty galaxies, far away, but obviously not as far as the cosmic microwave background, so along the line of sight. And then there's dusty point sources, radio point sources. There's the SODI, which is light that scatters off things in the solar system. So these are all things that you can see in the maps. And so some of them are just a nuisance. Well, depends on who you are, but if you want to study the CMB, some of them are just a nuisance. Others also allow you to learn something interesting about cosmology. So we can learn more about reionization. You can learn about clusters from the Sunyaev-Seldovich effect, and you can learn about structure formation, let's say, from the lensing of the cosmic microwave background. And so the one thing, the thermal SE effect, maybe let me say a little bit more than what's on the slide. So for the thermal SE effect, the basic physics is, so this is Sunyaev-Seldovich effect. And the basic thing that's going on is that you have clusters that are along the line of sight that have hot electrons in them. So if you look at the Boltzman equation, so this is again the Boltzman equation for photons. We're trying to understand what happens to photons as they pass through a galaxy cluster. And if you look at the Boltzman equation for photon and electron temperatures that are much less than the electron mass, then, kT is less than MEC squared, then the Boltzmann equation looks like this. So you have dN by dt is equal to the free electron density times sigma tau divided by ME, the photon momentum squared. Then there's d by dP of, so there is k TE P to the fourth dN by dp. This again is the photon phase space density or spectrum, plus, because for now I'll ignore the fluctuations in it, plus p to the 4 n of p times 1 plus n of p. This is what the Boltzman equation becomes, just from the collision term of scattering of electrons or photons in this limit. And in the limit that we're interested in now, the temperature of the photons is much less than the temperature of the electrons, because these are hot electrons that are in the galaxy cluster. So this contribution is the one that dominates. So this becomes dN by dt is equal to Ne Thomson cross-section divided by the mass of the electron divided by p squared, and we can pull out the kT because it doesn't really depend on the momentum, d by dp, and then p to the 4th dN by dp. And then we can also remember that we're interested in just small fluctuations around the black body distribution. So we have a black body spectrum that's passing through this galaxy cluster, and we're looking for the small distortion on the spectrum that this galaxy cluster generates. If you do first order perturbation theory, so we're expanding n is equal to n bar plus delta n. This guy doesn't really depend on time, so it drops out. So you just get delta n d delta n by dt is equal to, and then on that side you just have the black body spectrum, and we can pull out this whole thing. Well, let's write it like this: Ne sigma Thomson kT electron over me, and then we have this thing 1 over p squared d by dp p to the 4th dN bar by dp. So it looks like this. This is all time independent, so we can easily integrate this equation. So we just find that delta n is equal to this thing we can just pull out altogether. This is 1 over p squared d by dp p to the 4th dN bar by dp, where the n bar, remember, is just 1 over e to the p over kt minus 1. So this thing we know. And then this thing just is integrated over time. So this is the time where they enter the cluster, get out of the cluster, d tau, Ne sigma Thomson kt over me. This one you can just work out. The one thing to remember is that you can write it as a temperature perturbation, which is, so we can write delta n just as a Taylor series expansion as n bar prime of p times dN by dt delta t. And so that means we're just dividing this by this, and that gives you exactly what's written in the slide there. So that gives you, if you just plug that in for the black body function, you're getting this contribution. And then y is just this integral that we have here, except it's converted from the time to the path length, but that's just a change of variables. But that's what the SE effect is. So it's just an effect of that the hot electrons in a galaxy cluster have on the CMB photons. And so you see this is the Compton Y parameter, and so you see that you can make maps of the Compton Y parameter, which is a measure of the hot gas between us and the surface of last scattering. Does that make sense? Okay, so then this is what it looks like in the map. So if you look at a particular position, so this is Abel 2319, then this is the spectral distortion that you expect for the SE effect. So this is this function, this x hyperbolic cotangent x over 2 minus 4, where x is h nu over kt. And you see that you expect a deficit at low frequency, so there's some frequency where nothing happens. Well, physically, again, what's happening, maybe these shapes are kind of confusing at times, but what's happening is that you have a black body spectrum. It passes through some hot electrons. The photon number can't change, so to increase the energy, you just have to shift it up a bit. And then at low there's some neutral frequency here, which happens to be 217 gigahertz. And then at lower frequencies, you have a deficit, and at higher frequency, you have an increase. So this is kind of what it looks like. And then if you look at 44 gigahertz, you don't see much. There's a small decrement. At 70 gigahertz, it really looks like there's a shadow, something blocking the CMB. The same is still true at 143 gigahertz. And at 217 gigahertz, you don't see anything. You just see the CMB. You don't see the cluster. It's transparent. And then you see at 353 gigahertz, it emits. So you have hot spots in the maps above the neutral frequency and cold spots below. This is what it looks like. And you can look for that in the different maps across the sky and map out all the clusters that are there. So this is what is done to get the SE clusters. So you see they found a lot of clusters in this way. And with higher resolution instruments, you can in principle find many, many more clusters, hundreds of thousands of these SE identified clusters. And this is also something really that a lot of future experiments will be doing. And you can do some cosmology with it, or try, by measuring the power spectrum of this map. I mean, right now you need better, well, you need to deal with the CIB, so there's some other contaminations. It's also fun to really see it at the map level slightly better with the higher resolution instruments. So this is just a comparison of what WMAP looks like on a 50 square degree patch. This is what Planck looks like. So you see you get much higher resolution, but you're still not seeing the clusters by eye. But if you go to the higher resolution ground-based instruments, so this is from a 10-meter dish, you see that you really see these as little shadows, just little dots of SE clusters in the maps. Then there's also the white spots, which are the point sources that are just emitting. But these are the SE clusters that just block out some of or remove some of the CMB at that frequency. And you can then follow up on these clusters with optical surveys, or try to do various things. Lensing is another effect that's caused by the large-scale structure between us and the last scattering surface. So if you have objects, if you have mass, then the CMB photons can be deflected. They're deflected by some amount that's set by the gradient of the projection of the gravitational potential. And this is something that you can also try to reconstruct. So one of the effects it has is an effect on the peaks of the angular power spectrum. And this is because the angular power spectrum is a measurement over the full sky, but you can imagine that you have a measurement of an angular power spectrum just in a small region of the sky. So you can try to measure an angular power spectrum there, and then if you imagine you have a lens, it magnifies all the features there, which means that it shifts the power spectrum to larger scale. So you can try to draw it. This will probably fail, but I can. So there's something that you get when you, in the absence of lensing, let's say you had a power spectrum that looks something like this. Now you measure the power spectrum in a relatively small region of the sky that's magnified. This just means you're shifting everything to larger angular scales, or lower L. So you get something that looks like this, just all shifted to larger scales. There are also patches where you demagnify the CMB, so you shift it to shorter scales. And then if you do the full sky measurement, you're averaging all these things together, which eventually has the effect of smoothing out the peaks a little and filling in the troughs a little bit. So you're just averaging these things. So that's one of the effects. Another effect is that it leads to a correlation between the lensing of the CMB and the integrated Sachs-Wolf effect, because one of them has to do with the time derivative. The ISW we saw has to do with the time derivative of the gravitational potentials, whereas the lensing has to do with the spatial derivatives, and those things are clearly correlated. It's still coming from the same potential. The equations of motion correlate these guys. So there's a correlation, and this is something that's actually removed for the analysis of non-Gaussianity for Planck. So this is something that's subtracted. So there are 3-point functions that are measured in the CMB maps. It's not that you don't measure any, just no primordial ones. But there are, so it's reassuring in the sense that the ones you expect to be there are actually also there in the maps, and you have to then subtract them. And after you subtract them, you don't find any primordial non-Gaussianity. And it also leads to a temperature 4-point function that you can measure. So there's a number of effects from lensing, and using the 4-point function, you can make maps of that and compute power spectra, and it's been detected at about 40-50 sigma. So this is the measurement of the lensing power spectrum. So the power spectrum of the lensing field, not the CMB, but the lensing field. And you can also, as I said, you can make a map. So this is a map of it, and this shows you a projection of all the mass between us and the surface of last scattering, which by itself is kind of a cool object. So you can just measure or map out all the mass between us and the surface of last scattering. But the idea is that it's not just cool, but you can also try to use it for science by cross-correlating with galaxy surveys. You can try to measure the bias of objects in that way. So there's useful things to do with the lensing maps by cross-correlating with large-scale structure surveys. And it's also interesting in its own right because it's this map actually that will be used to measure the sum of the neutrino masses from the cosmic microwave background. Okay, so this is what I wanted to say about other effects that you can find in the CMB maps. Are there any questions about these parts? Yeah? So neutrino masses have the effect that they remove some of the power on small scales in the matter power spectrum, just because they're free streaming species, and then depending on what their mass is, sets exactly when they become non-relativistic, so that sets the free streaming scale. And you don't cluster on scales that are smaller than the free streaming scale. So there's a suppression, depending on the mass, there's a suppression of the matter power spectrum as a function of scale for different neutrino masses. So the larger, so as the neutrino mass, I'm not sure how to draw it, but as the neutrino mass increases, you get a larger suppression on small scales. And this is something that you can look for. This would suppress the structure here in this lensing map. So it suppresses the power spectrum on small scales in the lensing map. And this is something that you can try to look for. Does that make sense? Any other questions? Okay, so then the next thing I wanted to discuss is just how you actually use the data and do a measurement. And first we'll look at an ideal measurement for an instrument that doesn't really exist, that has no noise and infinite resolution. And then we'll try to see how the real-world effects enter into the measurement. So if you have an ideal measurement, you just have a map of the temperature fluctuations. There's no galaxy, nothing else, just CMB. And then you have Q and U maps. This is what they would look like if they were, I mean, for Planck I showed you, but they're quite noisy. So this is what they would look like without any noise. You see actual interesting structures. And the first step you do is what we discussed. So you just measure the multiple coefficients from the maps. So this is what the instrument would provide. This is what is usually given to you if you look at the data from the satellites. Then you basically Fourier transform or do this multiple expansion, and you just square these things and average them to compute the angular power spectrum. For polarization, as we saw, you compute the AELMs and you get the TE cross spectrum from this guy with this guy, and otherwise EE and BB. Obviously, you can also compute the TB and EB cross spectra. Nothing stops you from doing it. Usually they're 0 if your theory respects parity. If you want to do it in practice, I'm giving you some of the links here. So this is the code that you can use that does these calculations. So it takes a map and then spits out for you the ALMs, for example, or you can use use it to compute the CLs and so on. So that's the code that's usually used. This is the reference for this code. If you like Python, there's also a Python version of these things, so you can play with the Python version. Once you have the maps, what you want to do typically is estimate, and this is, I guess, something that you at some level learned already from other lectures in much more detail, but you're trying to estimate the parameters from your data set, and what you want to know is what's the probability that your set of parameters is correct given some data. And that's not something that we can directly compute, but what we can compute is given a set of parameters, what's the probability distribution for the data. So you can use Bayes' theorem to write the thing you want to know in terms of the thing you can compute, and then a prior and some probability on the space of the data that's usually just said to be a constant. And so typically you define a likelihood, which is given by this thing, and this is something you can compute. So that's and I'll show you some simple examples. We'll discuss more what this looks like. So the first thing is for the temperature anisotropies, if all you have are temperature anisotropies, we know that for the Gaussian perturbations, this is all there is. So we have, this is something that we looked at. So here I forgot the T's, but we always had the ATLM. ATLM was the CTT, delta LL prime, delta MM prime by rotational invariance. And this just tells you that these guys, if it's Gaussian, obey a probability distribution that looks like this. So this is just the usual Gaussian. You have 2L plus 1 of these things. This is what the probability distribution looks like. It's the exact probability distribution for your theory given the CL. So this could be your theory, or you can then write it in terms of the CLs as a function of the underlying parameters that you're actually interested in, like the omega matter, omega baryon, and so on. Often you're not measuring the ALM, so you're not necessarily interested in that, but you can easily go from a likelihood for the ALMs to a likelihood for the CLs. It's just a change of variables for the integral. So that would be the exact likelihood. If you had an experiment that does this kind of thing, this is the likelihood you should use, where these are the observed ones. This is your theory, the observed ones. So you can work out the likelihood just because you know the underlying statistics of your ALMs. It gets a little bit more complicated, but not too bad if you include polarization. So then this just becomes, you have a vector of these ALMs, and then these become matrices that look like this. So here again, the TB, EB blocks are 0, just because we assume that it respects parity. And then the likelihood just looks like this. So this is the thing that when you compute these correlators, just gives you back the matrix of the CLs. So that's the probability distribution. Or if you trade it in for the CLs, it looks like this. So this again is just a change of variables that you can do. And yeah, so then the question is, so now you had your maps, you created a likelihood. What do you actually do with the likelihood? One thing you can do is to just evaluate it on a grid. If you have only one parameter or a small number of parameters, that's relatively easy. Typically, you have models that have more than one parameter, so it's difficult to evaluate it in that way. So you use Markov chain Monte Carlo methods, and they are also readily available for these kind of analyses. So the one of them that's used a lot is CosmoMC, so that's the link if you want to play with this. And then there's also Monty Python, although this one, I think, CAM, CosmoMC, by now they also all have Python versions. The most commonly used sampling algorithm, not necessarily always the most efficient, but one that's very common, is the Metropolis Hastings sampling. So it's a very simple idea. Here you just start with some point. Doesn't matter, you just start with some random point, and then you pick another point and you compute the likelihood at the second point. Then you compute the ratio of the likelihoods for the 2 points, and if the second point has a better likelihood, then you keep that point, so you stick with that point. If you have a worse likelihood, so if the ratio is less than 1, then you don't completely throw out the point, you keep it with a probability epsilon. So this is basically like a thermal random walk, and then you just repeat and you sample that likelihood, and you can show that that eventually reproduces random points that are drawn from that likelihood. So that's the most common way to sample it. And from that, you then find the best fits, your means, your error bars, whatever you want, covariance matrices, anything you want to compute from this. Okay, so that's the ideal measurement. Are there any, yeah? The priors, that depends. I mean, it could be like if it's a measurement of, it depends on the measurement and what the prior knowledge is. So let's say you're doing a measurement with Planck. You might want to impose a prior, for example, on the Hubble parameter that's coming from the Rees et al. Measurement. So it's coming from a different measurement, and then you typically use the posterior for some other measurement as the prior for that one. And then for the cosmological parameters, usually you just take a flat prior on an interval that's not too wide, so you spend 100 years searching the parameter space because eventually you find a pretty small Gaussian peak somewhere. So typically for many parameters you just take a flat prior. Then there's still the question of how do you define your parameters. But for most of the parameters we know we just use omega b, omega cold dark matter, and so on, and you use a flat prior between, for omega cold dark matter, let's say 0.1 and 0.15 or something like this. I mean, omega ch squared. So depends on the parameter. And then if you want to take priors from external measurements like h naught, you just take the posterior from the other experiment as your prior. Or could be other priors, like from the BAO measurements. Sometimes you impose a prior on the, you take your other measurement as the prior. Any other questions about the ideal measurement? If not, then we'll try to look a little bit more at what happens in the real world. So in the real world, you have noise. That's always there, and there's always some finite resolution. It's also the case that these maps are pixelated, so you average your data into some pixels. This is something you choose, but you still have to correct for it, so you can make your pixelization scheme whatever you want. For Planck, there's something like 50 million pixels. But you can choose other numbers. I mean, but you have to correct for it. You mask because there's the galaxy along the way. So there's a number of real-world effects, and so let's look at how you include those. I mean, the simplest way of including them, it's not feasible, but the simplest way of including them is if you work with the map-based likelihoods, because there you know the statistics of your fluctuations. They're just Gaussian. So it's easy to incorporate them. So you just compute the 2-point correlation functions are just the covariance for the signal plus the covariance for the noise. It's very easy to include. This also includes masking. In other words, you're only looking at pixels that you didn't mask. So it's very easy to do. And the exact covariance matrix for what you're doing here, including masking, including the noise, including everything, is given here. And so in principle, this is something you can directly sample. So you can run your Markov chain Monte Carlo with this. The problem is really that the number of pixels you have is too high, so it's not something that you can in practice use at high resolution. This is used as you degrade the maps to low resolution. If you look at large angular scales, this is what's used, but on small scales it's just not computationally efficient. For polarization, it works in the same way. You just have a matrix everywhere. And so because it's computationally inefficient, you have to find other ways to make the measurement on small angular scales. And usually what's used is to use the likelihoods that are directly based on the angular power spectra instead of the pixel space likelihood. And so here what Planck used is a very simple approximation. You just assume that the likelihood is Gaussian for the CLs. Now it's clear that that's not really true. It's clear that if you had an underlying random variable like A that's Gaussian, and you take A squared, then the A squared, so CL, which is A squared, now satisfies a chi-square distribution with some number of degrees of freedom. It's 2L plus 1 because you have 2L plus 1 ALMs that make up a CL. So it's really a chi-square distribution, not a Gaussian distribution, but then at large L, by the central limit theorem, it should become a Gaussian. So if you're only interested in small enough scales, it's okay. WMAP corrected for the departures from Gaussianity for the chi-square distribution. They had some corrections to it. Planck didn't, so Planck is just using literally a Gaussian covariance matrix on small scales. And so the advantage of these kind of things is that everything is simple to calculate analytically. I'm just including it because the question came up and I sketched it on the board, but so here it is again. So you have your temperature maps, and then you want to mask them because there's the galaxy along the way. So you just downweight the galaxy. So you don't necessarily set it to 0 and 1, but you have some smooth transition, and you get some new map. That's I call delta T tilde when I was writing it down. And you can compute with the same heel picks, you can compute the ALMs for these maps. And you can also compute what are called the pseudo-spectra from these. These are not close to the theory CL, so you have to still do something with them, but you can show that on average, so if you take the ensemble average of these ones, they're related to the CLs that you're interested in this way. So there's a thing called the mode coupling matrix that you can compute in terms of what you did with the weighting. Then there's a pixel window function that comes because you're pixelating the map. And then there's the beam window function that has to do with the fact that the instrument has finite resolution. So the finite resolution is just a convolution of the data, which gives you a multiplicative effect in L space, and the same is true for the pixel window function. So this is what the relation looks like. And then if anyone is interested in it, I'm happy to discuss this more. I also have notes if anyone wants to see this. You can find some of these things in the appendix of the 2013 Planck likelihood paper, but you can analytically compute the covariance matrix for these things. Just looks like this. You can express it exactly in terms of the mask. There are some regions where the approximations used aren't so good, so you then use simulations. But in 2013 by Planck that wasn't done, so they really just used the analytic likelihood that I'm writing here, the covariance matrix. So we discussed the likelihoods on large angular scales, which is best in pixel space, and then we said they're inefficient, but and then we discussed something that works best on small angular scales. So the obvious thing is to create these hybrid likelihoods where you use the pixel-spaced approach for the large angular scales, and you use the L-based pseudo-CL likelihoods on small angular scales. And this is also in practice what was done by WMAP and by Planck. So both of these likelihoods actually matter. So now I'll just tell you a little bit about the data. I'm just showing you a picture of WMAP. Was launched in 2001, observed from L2, and ended its observations in 2010. So there's 9 years worth of WMAP data. And you can find the data. So I think what's nice about the CMB community is that basically all the data is public. It's much easier to play with the data than with the high energy community. So here you really go to this website if you want to play with it and find all the data for the 9 years. There's really basically everything is there. So there's things like the power spectra, but you can also get the 9-year maps. You can get each year's maps. You can get various products, the masks. You can also get the full time stream that's coming off the satellite in case you want to redo all the analysis. Not sure I recommend it, but it's something you can try. And so there's really a lot of data you can play with for WMAP. And also for Planck, which is more recent. So Planck, I'm sure everyone knows, it launched in 2009. also observed from L2 the second Lagrange point, and then it had two instruments. There was the high frequency instrument and the low frequency instrument. One of them, the bolometers, have to be cooled, so it eventually ran out of coolant and ended observations in 2012. LFI, the radiometers, they can observe longer and ended their observations in August 2013. And the nominal mission data was released in 2013 and the full mission data in 2015, and there was just another release of the data. There isn't yet everything out for the third release, so I'm showing you the second one, but eventually there will also be everything for the third release. The maps by now are out on the Planck Legacy Archive, but things like the likelihood aren't yet out. So it's still actively ongoing. The official page, maybe I should have switched it around. The official page is this one. This is the Planck Legacy Archive, and you can find pretty much everything here. You can click your way through. I often find this more convenient. I'm not sure I'm supposed to advertise this, but there's another website where you can find the Planck data. And either one, I mean, the data is obviously the same. It's just easier to find sometimes in one place than the other, but you can download pretty much everything there. One obvious question is whether WMAP and Planck agree, so at what level they agree. And they agree really well. So there was some discussion early on about relative calibrations and so on, which I won't discuss because this was all sorted out. But if anyone wants to know what was going on, I'm happy to discuss it. But the upshot is that they agree really well. So here I'm showing you the WMAP 94 gigahertz data, and here I'm showing you the Planck 100 gigahertz data. They're shown at, this is called NSIDE 512. This is just a feature of the HealPix pixelization scheme. So HealPix breaks up the sky into 12 basic patches. So there's, if I draw it, it's probably not going to work. But so you have a sphere, and then you have 4 patches that kind of look like this around the equator. And then the rest, there's 4 up here for this patch, and then 4 down here for the southern patch. So there's 12 basic patches, and then inside it tells you how many more times you subdivide. So each of them are divided a number of times. So the number of pixels is 12 times NSIDE squared. So this is what the NSIDE here means. And then you see that if you look at high latitudes, the maps agree very well. So all the spots that you find here, you also find them here. There's a small, if you look in the galaxy, you see that there's some differences. So you see some red here where you don't see any red here. So it's kind of fun to understand what that is about because it's related. Yeah? Sorry? Yeah? Yeah. Uh-huh. I mean, I'm not sure that my resolution is high enough, but certainly the maps have, yeah. And so if you take the difference, it looks like this. So the question you might try to understand is why there is a difference at all. So you see that indeed there is a difference if you look at the galaxy. And then the thing to remember is that when it says 100 gigahertz, it's not literally observing just at 100 gigahertz. It's some band of frequencies around 100 gigahertz. And similarly for WMAP, it's a range of frequencies around 94 gigahertz. So is there any ideas what could cause something like this? So let's erase and maybe draw a picture. So in frequency space, if you look at so there's band passes associated to them. Let's call them B of the frequency, nu, and then there's a central value somewhere around 94 gigahertz, and then there's a band pass that maybe looks something like this, and then there's 100 gigahertz, let's say, and the Planck band pass looks something like this. So the question is, how do you end up with a map that looks like this if you take the difference? Any ideas? So clearly there has to be something that emits positive, so something has to be emitting in the Planck band that isn't in the WMAP band, so, and it has to be pretty narrow, otherwise it would just leak over. So there has to be some line emission, and indeed there's line emission from carbon monoxide at 115 gigahertz, and this is what's seen here. So this is CO in the galaxy, and you can show that that's true by just taking really a CO map of the galaxy. So if you look at this, you can exactly reconstruct the CO emission. So they agree in that sense. And the additional thing to know is that Planck is just more powerful. So before I was showing it to you at NSide 512. So now we're going to NSide of 1024. So we're increasing the resolution. And then you see the WMAP at NSide 1024 becomes pretty noisy. You don't really see the structures all that well anymore. The reason you see more here and here is because of the scan strategy. So some of the points you just observe more than others. Whereas for Planck, the map still looks very nice also at 1024 and even at NSide 2048. Another way to show it is by looking at the uncertainty on the CLs, and you see that in the beginning it's dominated by cosmic variance, as we discussed. But then eventually the instrument, here Planck actually keeps going. This is still cosmic variance limited, but for WMAP the noise comes in. So you see there's really a significant difference between the two experiments. I mean, it's good because Planck was later, but it's really much higher, much lower noise levels and higher resolution also. In addition to Planck, you can also find the data for various other experiments on the Lambda website. So it's a nice website. It's also not just for CMB experiments. You can find various other things on that website. H1 data, various other interesting data sets. Okay, any questions about that? So that's the data that's available. And now I want to say a little bit about the measurement of the angular power spectrum, or how you would do that in what it looks like in practice, so in the real world. So the likelihood, as we already discussed, is a hybrid of a pixel space likelihood for low L and then this fiducial Gaussian likelihood for high L. Fiducial just means that you have some fiducial Gaussian model that you're using as a central value for your Gaussian. And here are the analyses, what they looked like for in 2013, 2015. So these are the pixel space likelihoods in polarization, and in the 2013 analysis, Planck relied on WMAP, which used 67% of the sky. Planck then used 47. Anyway, so these are the pixel space likelihoods. And then the higher likelihoods, there were slightly different likelihoods that were used in the different analyses, but these are the kind of likelihoods I described. So at the level I described here, they're kind of the same. There are small differences in how you model certain things. The likelihoods for the angular power spectra that were reported were really based on the 100 gigahertz, 143 gigahertz, and 217 gigahertz maps. And the spectra were used at 100 gigahertz up to 1200, 143 up to 2000, and then for the cross spectra and the 217 auto spectra out to 2500. And the reason the L ranges are different is just because for 100 gigahertz the resolution is worse. So the resolution, the longer the wavelength of the photon, the worse the resolution if it's diffraction limited. So you have a 10 arc minute resolution here, 7 arc minutes resolution here, 5 arc minute resolution here. And so you keep the spectra only up to where the noise isn't yet too crazy. So you keep it to 1200, 2000, and 2500 for these. This has to do with the noise and resolution. Then, as we said, you have to mask the galaxy and the point sources because you don't want to measure the CMB in those pixels. I mean, there is no CMB in those pixels. That in practice looks like this. So you also see that you don't necessarily have to mask the same pixels at all frequencies. You really just mask where you think you can't control the galactic emission. So for 100 gigahertz, because the foregrounds are lower, you can keep a little bit more of the sky than 143 gigahertz and 217 gigahertz. So these are the masks That's what they look like for the 2015 analysis. And even though you're masking a lot of the sky, so I mean this is the galaxy, this is large and small Magellanic Cloud, and then there's some CO emission, and then here are the point sources. So even if you're already masking a lot of the sky, there's also Andromeda, but anyway, so even if you're masking already a lot of the sky, then there's still residual diffuse galactic emission that you have to deal with, and this is usually modeled at the level of the, well, in the Planck analysis, you could do it differently, but in the Planck analysis, it's modeled at the level of the power spectrum. So you make a model of the diffuse galactic emission, and you also have a model for the extragalactic foregrounds that you just have as templates that you subtract. And then you use this analytic likelihood approximation. And the one thing that's still missing to make the likelihood, we saw that there was noise in the likelihood. So you have to measure the noise from the data, which you can do by taking the first half of your data, the second half. The CMB should be the same. If you take the difference, you should essentially be getting a measurement of the noise. And this is what that looks like. So typically, people will approximate the noise as white noise, meaning that n sub L is just constant. Planck's noise isn't really white noise, so if you look at 100 gigahertz, it looks like this. So there's a noise model that you can then fit to it to extract it. This is the noise at the different frequencies, and so those are the ingredients that go into the likelihood. Those are some of the things you have to measure. You also have to measure relative calibrations and so on, but that's what it looks like. And then you can calculate the likelihood with the formula I showed you a while ago. And this is what the covariance matrix, or the diagonal elements of the covariance matrix, look like at 100 gigahertz, 143 gigahertz, 217 gigahertz, and these are the 143 cross 217 cross spectra. And the orange, I mean the crosses, I'm just indicating what the scatter is that you reconstruct from the data. So you see that this analytic approximation works quite well. It matches the scatter that's seen in the data, which is good. And so then once you have a covariance matrix, you feed it into your likelihood along with the spectra, and then you just run your favorite Markov chain Monte Carlo and reproduce the Planck results. So this is a table taken from the Planck results. So that's what it looks like in practice. Are there any questions about these parts? Yeah?
What is that beta
This is essentially the peak positions. So this is the angular scale of the peaks. And that's a parameter. So if you look at it, you see that that's the parameter that's easily the best measured at the 0.047% level. And the reason that is because you're doing very well. I mean, you have a bunch of peaks in Planck, and you can measure the angular scale that's associated with that quite well. So that's why that parameter is very well measured. And then so that's that parameter. Often you translate it into some others, but in the code, that's the parameter that's used. And then MC, there's different definitions of it. So if you look at different papers, you may find slightly different thetas, but this is basically the peak positions in some way of defining it. And the others are clear. I guess this is omega BH squared, which we discussed for the baryon mass fraction, the cold dark matter fraction. This was the optical depth to the surface of last scattering, so which measures how many photons scatter off the hot electrons after the first stars form. This is the amplitude of the primordial density perturbations, and this is how the primordial density perturbations depend on scale. So if you write down the expression, then the power spectrum, often it's called delta R squared. Often it's written in this way, delta R squared of K, is equal to delta R squared of K star times K over K star. This is the pivot scale, so some scale that you pick. Typically, it's either 0.05 inverse megaparsecs or 0.002 inverse megaparsecs, and then to the ns minus 1. So this is the spectral, it parameterizes the power law for the primordial density perturbation. So this is something that you can compute in slow roll inflation, and you find that it's 1 plus order epsilon, so it's a small, it's not exactly scale invariant, and it departs from scale invariance at something that's now detected by, the departure is seen now at the 5 sigma level. And then a different way of writing it, so this is how WMAP was writing it, so often there was the delta R squared quantity. You can also write it as the scalar power spectrum. It's really the same, but scalar power spectrum is the scalar amplitude times k over k star to the ns minus 1. And so this is the ns that appears there, and it's typically 2 times 10 to the minus 9. And then, I don't know exactly why, but Planck always reports the log. Sorry? Sorry? Omega matter? Yeah, that's dark matter. So this is, if you take omega cold dark matter, yeah, it's related to these two. So the line here indicates that these are the ones that are actually measured in the fit, and these are derived parameters. So H0 is also not something that's directly measured by Planck. It's something that you infer based on lambda CDM. So this is lambda CDM, the 6-parameter lambda CDM model. And then you infer omega matter is omega baryon plus omega cold dark matter. So you would just add these two and divide by H squared to get that. But yeah? Sigma 8 is the amplitude of the matter fluctuations on a scale of 8 megaparsecs. So this is, if you look at this, a prediction about the matter power spectrum. So you can define the matter power spectrum, and then you can compute the density contrast in that. So the delta rho over rho of matter, delta of x, and you make a top hat average of that quantity on a certain scale, which is indicated here by 8, and then you compute the power spectrum of that thing. So delta of x, delta of, well, delta x squared. Let's say this is related to the variance of the averaged quantity. And you average it because otherwise it blows up on short distances. Right, and then the reason this is reported, the A times e to the minus 2 tau, is because that's directly the quantity that you extract, or that's well measured from the amplitude of the primary CMB anisotropies. As we said, it's suppressed by e to the minus 2 tau, and the problem is that this guy isn't well measured. So as a consequence, this is a quantity that's pretty well measured, because this directly measures the amplitude of the CMB on small scales. Any other questions? Yeah?
Sorry, I heard that there is a tension between the value, the sigma 8 value reported by Planck and using different cosmological proof. Can you please comment something about it?
Yeah, I can say a few words. So the value of sigma 8 here is something, as I said, that isn't directly measured, but it's an inferred parameter. So you get the measurement, and then in the context of lambda CDM, you can predict that number. That's the 8.29, in 0.829. Then there are other ways of measuring sigma 8, which is, so this is measuring the matter power spectrum, how much clustering there is on a certain scale. And this is something that you can directly measure from the matter. So you can, for example, look at weak lensing surveys, can directly measure how much matter there is along the line of sight. So you can measure sigma 8 from there. And they typically find lower values, so they find something around 0.7. You can also measure it from what I was showing you earlier. You can measure it from the SE clusters also have some information of how much matter there is, so you can try to extract it from different measurements involving, for example, also from X-ray observations of clusters. There's different measurements directly of the matter, and those all seem to be lower. Each individual measurement is pretty challenging. So for the SE measurement in the CMB, one of the problems is that you only have a few frequencies to do the measurement and figure out where your SE clusters are, and it's typically contaminated by the cosmic infrared background. So when you compute the power spectra, you're not necessarily measuring exactly the power spectrum that you wanted, plus the one you wanted, plus some contamination that you have to somehow correct for. So that measurement is difficult. Weak lensing always also had in the past had problems with systematics, and so these measurements are challenging. It doesn't mean, I mean, now people think it's under control. There were measurements also by the kids survey. Then I think George Efstathiou had a paper, problems with kids. Anyways, so so all the low redshift measurements find essentially a lower value of sigma 8. So there's a tension between the value of sigma 8 predicted by Planck and the value of sigma 8 measured at low redshifts. And there's another tension you might have heard that's somewhat possibly related, I don't know. So there's a tension in a similar spirit between the value of H0 predicted by Planck in the context of lambda CDM and the value of H0 measured in the local measurements, for example, by Rees et al. So the local measurements typically find a higher value of H0. So none of these tensions are terribly statistically significant, but I think it's interesting to keep an eye out and think about how you can explain them. Typically, the models people propose to explain some of these tensions have the problem that you introduce as many new parameters as you have tensions. Because, for example, there was one proposal that the tension between the different Hubble parameters could be explained by just changing the effective number of relativistic degrees of freedom, but then that makes the tension between sigma 8 as predicted by Planck and observed in the low redshift universe even worse. So you can then try to introduce another sterile neutrino that erases some of the structure. So it's not clear. I don't know that we have a good understanding of what's going on. What I think is true is that it's not necessarily too productive to think about it in terms of a tension of H0, just because Planck is not really directly measuring H0. So it would be more interesting to figure out what the tension is at the level of parameters that are actually measured by the various experiments. So there's a paper that's interesting in that context by Lloyd Knox, where he's instead of framing it as a tension between the Hubble parameters, it's a tension between the sound horizons that are extracted from different measurements. The sound horizon at last scattering is something that the CMB directly measures and measures very well. So I think it's interesting to think about. There are some tensions. They're not, I mean, in the particle physics community, I think, well, I don't know, could go one way or the other. Usually, even if there's a 3 sigma thing at 750 GeV, there's a ton, 100 papers on it, but in any case, so it's not terribly statistically significant. It's around 2 to 3, some people say 3.6 sigma. So there are some tensions. Any other questions? Okay, so the next thing I wanted to talk a little bit about before we eat is the gravitational waves. The search for gravitational waves in the cosmic microwave background. And the calculations are very much the same as we did in our POI model. We saw that there's a decomposition of the perturbations into scalars, vectors, and tensors. The gravitational waves are the tensors, so you can write down the Boltzman hierarchy for the tensor perturbations. So for the photons, obviously, you still have the same thing. What changes is that now you're looking at the tensor perturbations in the metric. So these are the gravitational waves. So really what I'm writing here when I'm writing this is that initially you have Dij, this was the piece that I had in the metric of x and t. This you can sum over lambda, the helicity states, integral d3q over 2 pi cubed, and then you can write that as the polarization vector Eij of q and lambda, and then you have some, often in the context of cosmology for those guys, it's called q and lambda, and then there's some mode function, usually there's the e to the iq dot x from the Fourier transform. And then in flat space, it would just be a plane wave. So there would be the e to the minus I qt. Here, there's some function dq of t. That's the thing that appears here, plus Hermitian conjugate. And then the other piece that's different is the source function. It's a little bit more complicated. It's really just complicated because people here still expand in terms of the Legendre polynomials. If you were to expand in terms of the spin 2-weighted guys, this would collapse again and be simpler. But in any case, for some reason, this is how it's written. And so you have the same hierarchy. Everything really goes through. You can calculate the angular power spectra in the same way by solving it. You do the same line of sight integration trick. You compute them. This is what they look like. So there's a contribution, essentially a constant contribution to the temperature anisotropies from gravitational waves. This is how WMAP and Planck were constraining it. So WMAP and Planck were just putting upper limits on this contribution of gravitational waves to the temperature angular power spectra. There's also contributions to EE, but the most interesting one is BB because the scalar perturbations are not predicted to contribute here. So in principle, the idea is that looking for B modes in the cosmic microwave background is a direct way of looking for gravitational waves. It's not entirely true in the sense that if you had vector perturbations from cosmic strings or something like this, they also generate B modes. Typically, they peak on much smaller scales. So there are some features here that are pretty characteristic of the primordial gravitational waves. But so that's the basic idea. And there was a claim, I don't know, some of you might remember, so there was a claim from from 2014 by the BICEP collaboration. So there was, these were their maps, this was the E-mode signal, and that was consistent with what was expected from simulations of lensed lambda CDM plus noise. But the B-mode signal they had in the maps wasn't consistent. It was larger than what was expected from the simulations. And for a while, people were excited and thought these are gravitational waves. Probably not spoiling it too much if I say that now we know that what you see here is just the dust in the galaxy. The maps are still, I mean, they were the deepest maps at the time. Now the same collaboration has deeper maps and is still working on it. So this is something I got interested in at the time because I worked on stringy models that predict these kind of signatures. But then the more I looked at it, so these are different foreground models I made. If you want to know more about foreground models, I can tell you more about those. But the upshot when I was trying to make the likelihood was just that you see that all the models you make are just consistent with the data. So it's, I mean, it's just dust. And this was confirmed by the Planck and BICEP measurements. I don't know why they showed it in this way, because if you break it up, you see that even the shape is correct. But anyway. So this was probably for political reasons, was my suspicion at the time, but I don't know why they made this gigantic bin here. And but so once you then know that there's dust, you can correct for it, and you can make more precise, put tighter upper limits on the amount of gravitational waves. And this is from the recent BICEP Keck paper that just came out. Even though it says BK15, it just came out. The reason it says BK15 is because the data that just came out only used data up to 2015, so they have 3 years of additional data already. And so here you see much tighter upper limits now, so it's less than 0.06, the tensor to scalar ratio at 95% confidence level, and it's ruling out things that everyone, this is basically what was everyone's favorite inflation model. I think m squared phi squared is just the simplest thing you can write down, just a free massive scalar field coupled to general relativity. So that made a prediction up here. We're pretty sure by now that that's not really how things work. But we'll see. So there's a lot of activity. One thing I just wanted to highlight is that even though the improvements don't look so dramatic, I mean, they look, not too bad, but also not too exciting. The point is that, as I said, the tensor to scalar ratio is constrained in 2 ways. One of them is from the temperature data. This is what WMAP and Planck used, so this is the contribution on large angular scales. And then it's also constrained by the B-mode polarization directly. And the two likelihoods are essentially independent. These are independent measurements, so you can, the likelihood we're usually reporting is really the product of these two likelihoods, and usually we think of obviously there just being one parameter controlling the tensor to scalar ratio, but you can introduce artificially one parameter that controls the amplitude of the tensor, tensor contribution to temperature, and one that controls the contribution to B modes. And then typically we look at that diagonal, but if you plot the other version, I think you can see a little bit better what's going on with the constraints. So this was before BICEP 2 came out. These were the constraints. These were the constraints from WMAP and Planck that all come from the temperature data. And there wasn't much known about the contribution to the B modes. And then with the BICEP data, it improved the constraints there significantly, but accidentally to the same level that it was constrained at in the temperature data. This also means that this will get better pretty quickly. So if you just take the BK14 data, it improves it significantly. And there's a lot of experiments that are going on and looking for this kind of thing. So these are the experiments that are taking data now, let's say now to 2021. And then, I mean, these are, this is the BICEP Keck experiment that I mentioned, the SPT. Then there is EBEX was a balloon. They never really had any usable data so far. Then there were, no, I mean, just for technical, I didn't mean it in a bad way. I mean, it's just really the case because the control froze. So they only have a ring in the sky instead of a proper map. And that's hard to use. You need crosslinks to actually make a map. This is ACPOL with the colorful Artacama receiver here. This is an instrument that just started taking data. I mean, this is obviously still an artist's rendition of it, but they're starting to take data at 40 gigahertz. This is Polar Bear. From the name, you can guess it wasn't always meant to be in the Atacama Desert. Then there is ABS, the Atacama B-mode search. So these are some of the instruments that are taking data. As time goes on, there will be new experiments. This is still technically part of stage 3. It's an experiment where all the experiments that are now in the Atacama Desert will come together and work on what is called the Simons Observatory. By now there's more money available for it. By now it's around $80 million. So this is an experiment that will happen. It's supposed to have first light in 2021. And then from 2026 to 2036 or so, well, actually right now we're planning either 4 years or 7 years. So 7 years, so probably until 2033. But the plan is to have one big experiment for the entire CMB community, looking for both primordial gravitational waves, but also effective relativistic degrees of freedom, neutrino mass. And there's also some hope that there will be a space mission. So we're working on a phase A exit study for Lightbird. For PICO, we submitted a study. This would be a probe mission is what they're called right now. Something like that doesn't exist, but the idea is that NASA may be funding these things, so we're providing input in the form of a study for this satellite. And so there's a lot of upcoming data. The thing is that it looks easy because you're just looking for B modes, but as you can tell from BICEP, it's actually challenging because even though the scalar modes at linear order don't produce B modes, the lensing does, and so do the foregrounds. And the challenge is that you're trying to use, so this is the actual data, well, not actual data, but this is the simulation, what the simulation looks like for CMB stage 4. And then what you're trying to do is distinguish this from this at 5 sigma. Okay, so that's the challenge. And it's a little bit better because you can remove much of the lensing contribution. So then if you remove the lensing contribution, looks like this, and you're trying to distinguish these, but you still see that there's a huge task to remove the foregrounds at the level that's required. This is a simulation I did for CMB stage 4 that suggests that this is something you can do. So this is based on simulations on simulations for the galactic foregrounds, for dust, for synchrotron, and then this is a component separation or foreground removal technique, and you see the residuals and the measurement. So the idea is that this is something that's actually doable, but there's still some, we'll see. If it all goes ahead and we get to do these measurements, then if R is relatively high, 10 to the minus 2, you get a really high significance detection. And the goal for CMB stage 4 is to reach sigma R, an uncertainty on R of 5 times 10 to the minus 4, which would, for example, be able to detect models in this regime and would be able to rule out anything that has a tensor to scalar ratio. I mean, it would put an upper bound on R as less than 10 to the minus 3 at 95% confidence level. And this is the CMB satellite study that we're working on. So here you see, if you go from the previous one to this, there was an order of magnitude added here to the plot. And you see that even at 3 times 10 to the minus 4, you get a high significance detection. So in principle, there is still quite some room to go and to do better. So we'll see which of these things we actually get to see. But I think something like this we'll probably see sometime in our lifetime. This is what the angular power spectra would look like. This is just a forecast I did for the Pico satellite. So the blue here is from the Planck satellite, and the gray bands here is the forecast of what it would look like with the Pico satellite. And you see that it's only all the way back here that the error bars are blowing up. So it's really a high precision measurement, and you're really nailing down the angular power spectrum out to very small scales. So there's still quite a bit of information left that one can extract. So that's basically all I wanted to say. And I mean, for me, it's been fun. I'm technically a string theorist, a high energy theorist by training, but I really enjoy working with the CMB data also. And it's really, the CMB has provided us with a lot of information for the last 53 years. And I think at least for the next decade, we'll still learn quite a bit about also fundamental physics from the CMB, which I think makes it so much fun. So the one hope is that we'll get to see primordial gravitational waves with some of these instruments. What we will for sure measure with them is the sum of the neutrino masses and the number of effective relativistic degrees of freedom. And there's also interesting ways to put constraints on all kind of things, on interactions with the dark matter. There's plenty of things that one can do with those data sets. CMB isn't the only thing. So in particular, if you're trying to constrain non-Gaussianity, large-scale structure surveys will be interesting, because the CMB, even though we're going to do better, we're not going to, on some of the things, we're not going to do so much better than Planck. It's a factor of 2 to 3 better on various constraints on non-Gaussianity. But for some of these things, large-scale structure surveys will be quite interesting. But all in all, I think cosmology over the next decade should be interesting. And so I hope you enjoyed the lectures and you learned a little bit more about the CMB, and maybe some of you play with the data. So thanks. Any more questions, or lunchtime?